my screen. So this talk is going to be a bit about web bundlers and Webpack. In fact, can everyone hear me okay? Can someone just say hello? Yep. Okay, great. Okay, so yeah, Webpack is traditionally a bit of a black box for most developers. Tools like create React app, abstract it away and hide it. And this came from some research I was doing into web bundlers, Webpack specifically, and I found some interesting things and some kind of key concepts that I thought were worth kind of sharing and getting others to kind of get some insight on. So first off, a bit about me. I'm producing kind of an under the hood of series, which this is actually a part of. So far, I've done a couple on TypeScript, on Mocha, on React hooks and source maps. I've got a couple more ideas for things. So check my site for more at craigtaub.dev. Shameless plug. I'm, as Adam said, a member of the Mocha core team for a little over 2 years. So I'm a big advocate of testing and open source. And I've got a big passion for football. I support my local championship club, QPR. So the plan for today, we're going to start with what is a web bundler, then look at building a compiler for a web bundler. And this is going to be a real simplification of how Webpack works. There are lots of ways to solve this problem. And hopefully this way will offer some insights into the mechanisms that are involved. And then the final step will be using the output with a compiler. So something that I think is worth touching on first is, why bundle in the first place? These discussions, this question always comes up again. So performance reasons, third-party code is expensive. We can use static code analysis to optimize things. So things like cherry picking and tree shaking. We can also simplify what is shipped by turning 100 files into one, limiting the data and the resource expense on the users. Arguably, HTTP2 makes devices more capable of requesting dozens of files at once, but it's still expensive and it takes a toll on the user's time and the data usage. There are support reasons. The web has so many different environments, and you want your code to run in as many as possible while only writing it once. So adding polyfills where necessary. User experience. You want to utilize browser caching with separate bundles. For example, having a vendor for your libraries that you can cache for a long time, and then an app for your application itself that busts very, very quickly. And then lastly, kind of separation of concerns. You can really manage different ways how you serve fonts, CSS, images, as well as JavaScript. So the basic architecture of a bundler is essentially putting modules through a compiler to produce assets. Not really much else to say there. So before we start, there are a couple of items involved. And this is the thing which I think makes it interesting, in my opinion. There's lots going on in a short space. We've got an IFI, an immediately invoked function expression. There are pass by reference. There are dependency graphs. We're defining a custom import and export system, which is completely taken from Webpack. There are recursive functions. There's some AST parsing and generation. AST being turning source code into its tokenized form, so taking it from code or string to an array of objects. There's some hashing involved, and also with native ESM usage. So we're going to be using Node 13+, so we get the kind of native ESM functionality and its compile time checks. It's important to mention that I'm going to be ignoring non-JavaScript stuff. So CSS, images, fonts are not going to be touched on today. So the compiler, there are a couple of simple parts to it, including making use of the output. Step one is going to be traversing the dependency graph. We're going to be taking in an entry file and spitting out a dependency array. Step two is converting the tree into a JavaScript application bundle. So we're going to be taking in our dependency array, spitting out a bundle string. And then step three is helping our application make use of this bundle. So we're going to be spitting out a bundle file and a JSON manifest. So I've tried to stick to how Webpack does it. So our application, it's very simple, consists of 4 files. It starts with file A on the left with the main function. Its job is to get a datetime string. You can see that on line 5. And it gets us from file B on the right. Then it hands that to logDate function, which is on line 6. And it gets that from file C, which is at the bottom. File C's job is to add text to the date and send that to the logger, as you can see on line 4, which is found in file D on the right. So you can see it's very simple. It grabs a datetime string and it logs that with a message. So here is our application tree. File A calls file B and file C. File C calls file D. So starting with phase one, traversing the dependency graph. The job is going to be to take in an entry file and output a dependency array. So here we have a depth graph function to do that. Let's walk through the code. So we're going to be determining the file's full path early on, so line 4. This is very important, so it's clear at any point if we are dealing with the same file or not. Then we return early if the dependent already exists in our depth array on line 7. If not, we grab the file contents using the read file sync on line 10. We pass this content into AST, and I'm using a third-party tool for this. It's the AST library, and you can see the AST.pass on line 11. And then we store both the file path and its AST onto a module object, and that's on line 12. We add that object to the depth array on line 18. We've done this so we can build up our tree with the entry file appearing first. And what we're doing is we're going to process the dependence of the contents. So we map over the source.body, you can see on line 21, that holds each block of code. And then we check for the AST import declaration value. So those are the node types which are for an import statement. And then what we do is we recursively call this function with the value on the import, which will be the file name. This means it's a depth first search. So we're going to be following one of the branches of the app tree as far down as possible and then move up and right by one at a time. Interestingly, we could process the depths and then add the module to the depths array. This would produce a slightly different order in the dependencies tree and would mean that the application starts on the last item, not the first. And it's just easier dealing with it at the first. I actually found it works both ways, but it's just less complex to go this route. So our application tree now looks like this. On the right, we now have an array of objects. Each object is the file path and its source. So you can see file A, file B, file C, file D. Had we processed the depths before pushing to the depths array, it would have been in the order B, D, C, A, as the encode paths would appear higher. So onto phase 2, converting the tree into a JavaScript application bundle. The job is to take our dependency array and produce a bundle string. So this is where a large bulk of the work is going to be. So let's first touch on our compiler's job. Our compiler's job is to execute code which will produce executable code. That means we will have 2 levels of code, so we'll review them one at a time. First, we will review what the compiler builds, then review the built or the outputted code, which is then run by the browser. Hopefully that makes sense. So first, the building code, and starting with templates, which is something Webpack makes use of. On the left is our modules template. It's a simplified version of Webpack's modules template. Our modules template's job is to convert a given module into a module that our compiler can use. So let's look at the code. We hand it the module code and an index on line 1, see on the left. Webpack also does this with the index, and you can actually see this in the comments. In Node.js, all ES modules are internally wrapped in a function attaching runtime details, which is the exports. So here we are doing the same. Right now, you can see the module argument inside the hard-coded function on line 3, and that is going to be given an exports property, which comes from the runtime template. But don't worry about that now. We're going to be going into greater details on this in the next section. Again, this is something that Webpack does. And we want the code to be as compatible in as many environments as possible. And ES6 modules support strict mode natively, but ES5 modules do not. So we have explicitly defined strict mode in our module templates for each module, and you can see that in line 4 of the code. Again, this was taken from Webpack. On the right is our runtime template. Our runtime template's job is to load what will become our modules string into an array. And you can see that on line 35. All we're doing is taking it and injecting it into this string in its location that looks like an array. We will review what this code is doing later once we have the modules code inside of it. So Now onto our custom import-export system. We have two functions here. We have a getImport and a getExport. Their job is to swap AST with different AST that will produce our import or export system once it's converted back to source code. So to swap code that's using a native system to our own custom-defined import and export system. So if we look on the left, we will be producing code that you can see in the bottom comment on line 3. So you see the sum import equals the underscore our require bit. That's effectively what the AST, once it's transformed back to code, is going to look like. So it starts on line 7 by grabbing the name of the variable that we are going to be importing into. For example, with the comment, it would be the sum import. Then we get the value of the import, which is the file name. We transform that back into its full path and grab the index of that path in the depths array. As you can see on line 10, we get the item ID. So we will return AST, which includes the item ID and this import function name variable. And this is the thing that produces the code snippet like you see on line 3, but it's going to have our variable name and our import function there, and our ID there, importantly. On the right is the export function. This grabs the name of the variable which we export. So for example, as you can see on the comment on line 3 on the right, sum function. So this function then returns AST, which sets this variable as the value for the module.exports. So this function will return AST, which will produce the module.exports equals and then module name. We will be making use of these in the following slide. It's worth noting that Webpack stores dependency IDs on the module earlier, and it has its own dependency template, which is not something that I've done for this example. And what that does is it replaces the imports and exports usage with a custom variable. So mine just swaps the import and the export itself. Theirs swaps the entire line and all usages of that variable. So that's one of many things which aren't exactly the same as the real Webpack. So onto the transform. The transform's job will be to take our dependencies array and return a bundle string. So this is where it does the bulk of the work and makes use of the functions we've defined previously. So let's go through the code. On line 2, our transform function iterates through the dependencies array. You can see the reduce. Then it maps over the AST body for each dependency. See that on line 3. Then we're looking for the import and the export declarations on line 4 and on line 8. And we're going to replace each import and export it finds with our own. And you can see that we're calling the functions from the previous slide. We've got the getImport on line 6 and the getExport on line 10. We then replace the current AST with the new updated AST on line 14. So we're reassigning what body is. And then on line 17, it turns the AST back into the source code and builds a module template string from this code. We push this string to a new updated modules array. So that's what the reduce is doing. It's now building this array of all these module template strings. And then finally, on line 26, we join all the module strings together, see the join, and hand them into the runtime template. We would have had to give the last item in the dependency array if we had chosen to process the depths and then add them to the depths array, as I mentioned much earlier. But because we didn't do that, we don't have to worry about its order in the actual array. We know it starts at the first item. So now the code which is outputted from the compiler is here. Don't worry, we'll go through it. So the left-hand side is our runtime. It's from the runtime template. Nothing has changed here. The right-hand side shows all the modules which are loaded. Apologies about the bad formatting. But what you can see is that there are modules which we started with at the beginning found. So file A, as you can see, is in index 0. So starting on line 36, that is our file A. File B is index 1. You can see it starting on line 52 or 50. File C is in index 2. And then file D is found in index 3. So what's going on? Let's step through the code. The runtime template IFI runs immediately, handing the modules array as an argument. So it passes the array on the right as modules on the left. And you can see the argument on line 2 on the left there, the modules. So if we continue looking on the left now, we define a cache, which is called installed modules, and we define an import function. So here it's the underscore our require. So let's look at the our require function, starting on line 5. It checks if the module with that ID is in the cache already. If so, it returns its exports. If not, on line 13, it creates a module object and assigns the ID as the module's index and creates an empty exports object. The module index actually correlates to the location in the module's array, which actually correlates back to our initial dependency array. So moving on, and then on line 19, executes the module template function with the module and the require function as arguments. So you can see we're calling, based on the module ID, we then call it with the module and the underscore our require function. This will execute the runtime of the module, assigning the variable onto the module.exports. So we can see an example in index 1 on the right. If you look on line 55, we're assigning the return date time to the module.exports. So that's the module and the .exports that we are handing. It's from our runtime engine on the left. So this is a use of the pass by reference functionality. And all of the imports inside our modules will now utilize our custom method. So you can see an example in index 0. So if you look on line 39 and 40, it calls the new dependence with index 1 and it calls index 2. And then finally, back on the left, we cache the exports and return the exports for that module on line 26. See that? This way, the modules on the right can call the module they need by its index, and it returns the exports. Lastly, back to the function on the left, we execute the new import function with our entry point. So you can see on line 30, we're calling the require with index 0. This is hard-coded, which will start the application as it doesn't require calling an export itself. So I know there's a lot kind of going on there. That's kind of the bulk of the engine. Hopefully that made sense of having the runtime template and the modules template and how they work together. On to the final phase, which is helping our application make use of this bundle. Its job is to take our string in and produce a bundle and a manifest file. There's not really much to this phase. So now we have created a vendor string. That string that we had produced from earlier is a vendor string. So we want to use it. So first, we create a hash of the vendor string contents. See that on line 4. This is then used in the bundle file name. You can see line 6. We write the vendor string contents to a new bundle with the hash in the name. So we're writing a bundle with a hash in the name, and its contents are our vendor string, everything we produced previously. Finally, line 8, we write a manifest with the bundle file name in, so that we can access it. The last thing we do is we run a small Express server application, which pulls the bundle name from the manifest, and you can see that on line 2. And then we expose the build code under a static root on line 15, very kind of standard Express stuff. And the index page returns HTML with a script tag, which downloads the bundle. And you can see that on line 8. We call the manifest.bundle here. So if we were to run our typical npm run compile, npm run start, our application will build and then we'll run. The application will build and then the server will run using our application. And we can see our bundle and its contents in the network tab. So we can confirm it's worked by checking the console. If you look down there at the bottom, I ran it on Sunday. It is logged the date with our message. So it's kind of proven that there's the bundle and there's the date time and there's the string and it's logged it. So we can prove that it's worked. So finally, you could ask, what else does Webpack do then that ours does not? As mentioned earlier, there's this kind of full variable control. We just replaced the import and the export statements using our get import and get export functions. Whereas Webpack replaces all instances of the variable, so it maintains that control. I believe this functionality is very important for some of the more complex things that it can do. Handling non-JavaScript assets, so CSS, images, and fonts. Ours can't do this. Having a dev server and hot module reloading. This is all comes built into Webpack. Chunks. Webpack can put different modules into different chunks, and each can have slightly different runtime and polyfills if necessary. So you can have a vendor chunk, you can have your dynamic imports chunk, all with just the code that they need bundled into them. Multiple exports. So ours was just returning a function each time. Ours could do this, but it would need a defensive check on the module type. So whether it was actually an object or whether it was just a function. So it wasn't really worth it for this proof of concept. And then lots of further optimizations, things like minification, code splitting, cherry picking, tree shaking, and polyfills. Source maps. Webpack, when it uses a mixture of all the different pre-processes, the typing, the web, typing, any kind of pre-process, Babel, which they all generate their own maps, and Webpack manages kind of merging them all together. Ours kind of ignores all the source maps. And then lastly, there's making it extensible or configurable. Webpack has got loaders, plugins, lifecycle events. Interestingly, Webpack is about 80% plugins, even internally. So the compiler is firing hooks on certain lifecycle events. So for example, the pre-process of a file, so before it processes a file. And the loaders listen out for this event, and then they run certain function when appropriate. So we could extend our compiler to support kind of lifecycle events. We could use the node.js event emitter and fire on certain events. But again, it didn't seem worth it for this kind of proof of concept. So that's it. I hope this was useful. I learned a lot from doing this, from my own research. There is a repository if anyone is interested to go and download it and run it yourself and tweak and play around with it and see if there's anything else that can help you. And also there are more under the hood on my site on craigtaub.dev. So thanks for listening, and I will now take a look if there are any questions. So nothing in the Q&A yet. Maybe I'll scroll through the chat, see if there's anything.
Someone made mention of sort of what were you doing on line 13 or something like that. But
I'm a little confused as to where module ID on line 14 is coming from. Let me go back. ID, I'm guessing it's this guy. Yes, so module ID is an argument that is handed by the caller. So the modules exist within this array, within this modules array on the left, and they come from our ifs argument. And actually, they're only really invoked when they're needed, when they're called. So the runtime, yeah, I hope that. And like an example is that you can see that the rRequire runs calling 0. So that's like a very hard-coded example, and it knows that module ID is 0. It's not going to be in the cache, and it will then find module 0 in index 0, which is index ID 1, which is our main, our file A on the left on line 37. Hopefully that made sense. Let me see if there's another one. Any other questions? I can't see if there's any other. Actually. Oh, the QA. What you would do further? Interesting. So I guess if I go back to what we're missing, for me, the exports would probably be the easiest thing to do, but it's not very exciting. I really think that a lot of the chunking is very exciting. Being able to establish different runtimes, different polyfills, based on maybe 3 of your modules are using a certain library that the others don't need, or even an environment that the others don't need. Writing some logic around how that works and trying to establish different bundles and different chunks and different runtimes is probably the next step I would go. But I haven't looked into that further. That's probably what I think that would be an interesting one to look into. So if anyone is interested in doing that and pushing a PR, that could be really interesting.
Excellent, Craig. Well, thank you very much for your talk, and that is a deep dive indeed. And